All right, so we're starting here into 4.5 where we're dealing with trying to find solutions to quadratics that, aren't easy to find. So let's imagine that we had a parabola that crosses, I'm doing a bad job of drawing that, right there and there, okay? It's not at -1. You can see that crossing there is just shy of -1, and this crossing, it's not at +1. Now that doesn't mean it's not factorable or solvable by some other method. We learned last time how we could find values that were like 1/2 or 3/5. Those were things that we could find as long as they came from a factorable problem, and those would have looked like 2x minus 1 and 5x minus 3. If that was how it was factored, we would get answers like x equals 1/2 and x equals 3/5. Those are still solvable by sort of a factoring method to be able to find these solutions. However, if by chance these solutions occur at numbers that we consider irrational, meaning they can't be written as fractions, then we can't factor it. There were those problems that were non-factorable. It's entirely possible that we have a non-factorable problem that has solutions we should be able to find. Now, there's a possibility. What if that number there was the square root of, 1/7? Like, what is the square root of 1/7? Or over here, let's say it's somewhere between 1 and 2. If it's at 1.73 and so on, there's a number that goes on forever that's the equivalent of the square root of 3. What if that's where it crosses? Factoring is not going to produce these square root values. So we need to be able to manipulate square roots and use that methodology to be able to find solutions when they're not nice rational numbers. So we're going to talk a lot about what are we going to do in order to simplify and manipulate square roots. One of the first things that we need to understand about dealing with square roots is that a square root is defined as asking a question that what number times itself produces this result. In other words, the square root of 9 is 3 because 3 times 3 equals 9. Or it could be said that 3 squared equals 9. And we learn that a square root and a square exponent are opposites. Similar to the way that a plus and a minus are opposite, or a multiplication and a division are opposites. We'll learn a lot more about that in Chapter 6, but for now we're talking about the fact that these are opposite operations. So anytime we can produce a multiplication of the same number, we can say that we would know the square root of that multiplication. Another way to say that is, if I ask for the square root of, let's say, 7 times 7, well, the square root of 7 times 7 would be 7. Now, if you're not confident of what I mean there, let's look at the square root of 49. Because 7 times 7 is 49, and we know the square root of 49 is 7. But this right here, whenever we can produce that, the square root of that number is itself. Okay? The square root of that multiplication is the components or the product, is one of those factors that's duplicated. So let's look at a couple of other examples that might help us in this. Let's say that we had the square root of something that isn't a perfect square. Those are the ones that we're really concerned about. Let's say we had the square root of something like 150. 150 is not a perfect square. I know 121 has the square root of 11, and let's see, 196 is like 14. So the answer would technically lie somewhere between those. I could narrow it down. 144 is 12. 169 is 13. And there's one there. Is 13. So it looks like I'm somewhere between 13 and 12. So If I needed a decimal approximation, I know it's between 12 and 13. However, I don't want to approximate these square root values if I don't have to. We want to be able to manipulate them by hand and make them a little simpler to work with without turning them into decimals. So the way we're going to do that is we're going to split this into numbers that we do understand. The most basic way to do this is to just start dividing it by numbers that definitely go in. Like I could do 2 and 75. And then I'd split it again and get 3 and 25. And I'd split it again and get 5 and 5. I don't need to split it down to a 1. That's not important. But now I have these component pieces, okay? If I combine them together in one square root, I can think of it as 2 times 3 times 5 times 5. I'm going to show you another way to do this here in a second that might save you a step or two. But whenever I see a number multiplied by itself, that's a great thing for me. I can separate square roots into separate square roots, like the square root of 3 times the square root of 6 is the same as the square root of 18. That multiplication, and I can pull it apart, I can push it together. It's going to allow me to write this problem as the square root of 5 times 5 times the square root of 2 times 3 is just 6. It doesn't have that duplication, so I'm going to combine them. We learned over here that when you have a multiplication of the same number inside a square root, that number comes out. We're going to have 5 times the square root of 6. That's often written as just 5 root 6. Let me show you a couple other ways to do the same thing, but think about it maybe a little bit with a little bit more sophistication. Okay. Oftentimes, instead of doing 5 times 5, we'll put a 25. If we recognize that our perfect squares are 4, 9, 16, 25, 36, 49. The more of those you know, the easier this can be to recognize. So when I was dividing this 150 up, maybe I went and divided it by 25 at the beginning. That square root of 150 probably could have been split as 25 and 6. At this point, if I put both of them in a square root, I know the square root of 25 is 5. And that I still don't know the square root of 6, so that's my leftover piece. So there's a couple of ways to get here. If you want to take this other approach that's a little bit more direct, you have to know your perfect squares. And you have to take the biggest perfect square you can, or you're going to end up with some missing information there, okay? That's really what we're after. There are some specific issues that we have to deal with. I'll talk about one other specific issue that's going to come up. And it has to do with the fact that mathematically we have certain rules and policies that we try to adhere to and follow as much as we can. And one of those rules that we try to follow and manage is the fact that we're really not supposed to keep square roots in the denominator of a fraction. Square roots are hard enough to understand as they are when they're decimals. It's another thing to put a decimal in the denominator of a fraction. It's just messy, especially if you're trying to approximate it. It's difficult to work with. So when we have things like 3 over the square root of 5, I really don't like that square root down there. But I know I can multiply the top and bottom of a fraction by any consistent value. It's the equivalent of multiplying by 1. Well, if I could turn this square root of 5 into a number that does have a square root, that'd be really convenient. So I could multiply by the square root of 5, and what would the denominator become? It would become the square root of 25, which I know is just 5. So by multiplying by the exact same value, I'm able to cancel that square root out. But to do that on bottom, I did have to multiply through the top, and 3 times the root 5 is just 3 times root 5. This is an equivalent result to our original, but it doesn't have a root in the denominator. That's a pretty quick, easy thing to do, and it would be great if that was all we ever had to mess with. There is one other type of root in the denominator that we need to manage, and it's when that root is involved in addition or subtraction. So let's say I had 2 over 3 minus root, let's say 5. Actually, let's make this top number Let's just make it a 7. There we go. Sometimes I don't want to get too carried away with little details, but let's do that. The problem here is that if you try to times by root 5, okay, just for a second, think with me, root 5. That root 5, when I distribute, will make this root a 25, which we know the root of, but it also has to distribute to the 3, which creates a 3 root 5. And that keeps a root in the denominator. This doesn't work when there's addition or subtraction in our denominator. So instead we have to use something different. And this something different is what's called the conjugate. The conjugate is the perfect partner, and it has a lot to do with the difference of squares. If you remember how a difference of squares factors, like x squared minus 9, it's x plus 3 and x minus 3. This is the pattern we want to build when we're using a conjugate. I see I have 3 minus root 5. That means I need 3 plus root 5. So I'm going to multiply the top and bottom by 3 plus root 5. On top, it's just a multiplication that you just distribute and deal with it. 3 times 7 is 21, plus 7 times root 5 is 7 root 5. Nothing fancy going on there. On the bottom, we do have to FOIL. At least we think we do. Let's be real cautious here. Let's go 3 times 3 is 9. 3 times root 5 is a positive 3 root 5. A negative root 5 times 3 is negative 3 root 5. And negative root 5 times positive root 5. Okay, first, acknowledge that it's negative. And then square root 5 times square root 5 is square root 25. Okay, let's go through and do a little look real close at some things and clean a few things up. First off, a 3 root 5 minus a 3 root 5, those will cancel. That should always happen. That leaves me with a 9 minus, and what is the square root of 25? 5. This can be simplified, but I want to stop here and I want to acknowledge something. When we multiply by the conjugate, we do multiply 3 by 3. That multiplication must happen. And then, because we have a negative times a positive, we will always be subtracting. Root 5 times root 5 is square root of 25, which is just that 5. So you can find the pattern in this pretty easily to make it easy to simplify. I get 21 plus 7 root 5, sorry I'm writing kind of sideways, all over 4. That is our other issue that will come up, and we'll deal with it there. All right. Good luck. When you get into the homework, just kind of pay attention. I'll try to do one from each section to make sure it's clear what's going on. This is big stuff. We're getting into some heavier stuff as we go through the chapter, so it's important you ask questions along the way. Good luck, and we'll see you in class.